Pocket number 24. Charge Q is distributed uniformly throughout the volume of an insulating sphere of radius 4 centimeters. Alright, so we got a sphere. Whoop. Wow, I cannot draw. R equals, that is not a 4, that is a 0. 4.0 centimeters. Alright. At a distance of r equals 8 centimeters from the center of the sphere, so that's like out here. Little r. The electric field due to the charge distribution has a magnitude of E equals 940 newtons per coulomb. What are A, the volume charge densities for the sphere, and B, the electric field at a distance of 2 centimeters from the sphere center? Alright, so this problem is going to be exactly like the one that we just did in number 21, but now instead of being completely inside the sphere, we're going to be looking outside of the sphere. So if we look at our good old Gauss's law again, integral of E dot dA equals Q enclosed over epsilon naught, vector, vector. So again, here we're looking at spheres. Our electric field is radially outward because it's a positive field. So out here, our electric field is coming out normal to that outside sphere, which goes all the way around, but it's a small piece of paper. Can't really draw it that way. All right, so electric field is coming radially outward, so it's normal to the sphere surface. dA, by definition, is normal to the sphere surface as well. So at any given point on the sphere surface, E and dA are parallel to each other. So that means we can write this as the integral of E dA, or a dot product just turns into the magnitudes of Q enclosed over epsilon naught. Alright, so again, because we're a sphere, we're at a constant radius all the way around our Gaussian surface, or wherever we give a crap about the field. Our E is constant, so we can pull it out of that integral. So we get E dA, which is equal to E times A equals Q enclosed over epsilon naught. Alright, so here's where it gets a little bit different from the last one. This A over here is always the area of Gaussian surface. So that's where you're measuring the field. So that's going to be a spherical surface at 8 centimeters. Q enclosed is going to depend on how much of this junk is inside of this sphere. So in the last problem, we were taking a tiny little sliver inside, and now in this one, we're taking the whole thing. So our areas are going to be different. So the area of a sphere is 4 pi r squared. And just like last time, our Q enclosed is going to be density times the volume, right? But this time, the volume of our charge enclosed only goes out to 4 centimeters. It does not enclose this entire 8 centimeter sphere. Cool? So that's going to be 4/3 pi big R cubed over E naught. So that's the fundamental difference between this problem and the last one. So in the last problem, we could use little r also because it was being cut off by wherever we were looking at our field. Here our field is outside of the charged area, so our Q enclosed stops here. Okay, so again, our 4 pi's cancel out, but our r's don't. What are we solving for again? Oh yeah, density. So we're solving for rho. So we have E times little r squared is equal to rho big R cubed over 3 epsilon 0. So if we solve for rho equals 3 epsilon 0 electric field little r squared over big R cubed. So if we plug in our numbers, 8.85 times 10 to the minus 12, I forget the units always because I suck. Electric field at 8 centimeters is 940 newtons per coulomb. Little r is our 8 centimeters, so that's 0.08 meters. Wow, I can't talk today. Over big R, which is our 0.04 meters cubed. Alright, so if we come over to our handy dandy calculator, we get 3 times E naught times 940 times 0.08 squared over 0.04 cubed. So that's going to give us a density of 2.5 times 10 to the negative 6 coulombs per meter cubed. Alright, so for part B. Part B is find the electric field at a distance of 2 centimeters from the sphere's center. So that, going back to here, E times 4 pi little r squared is equal to rho times the volume over E naught. So now 2 centimeters is inside the sphere, right? So our Q enclosed is only going to be this part. So that means in our volume, when we're multiplying it by the density, this is going to be the volume of that tiny little part. So that's going to be our 4/3 pi. But now we're using little r again because we don't have this empty space. It's just this part. So this radius that we want to find our electric field at is the same as the radius that's enclosed, or is enclosing our charge. So hopefully that makes sense. If not, come see me, it'll be fine. Alright, so our 4 pi's cancel out, 2 of our r's cancel out. So our electric field is rho times r over 3 epsilon 0. So that's 2.5 times 10 to the minus 6 coulombs per meter cubed, times r is now 0.02 meters over 3. Epsilon 0 is 8.85 times 10 to the minus 12 units that I can ever remember. So if we plug that into our handy dandy calculator, 9.02 divided by 3 epsilon 0 squat. Electric field is 1880 newtons per coulomb. Blam, blam. And the end.